Okay, folks, so as promised, we're going to look at another equation of state known as the virial equation of state. And I really like this one because it allows us to actually explore the attractive regimes as well as the repulsive regimes. So starting with all relationships that we know here, we've got the compression factor, we've got the definition of molar volume, and we've got our ideal gas equation. The virial equation of state is put together by trying to apply some type of empirical relationship to the compression factor. So if I rewrite the ideal gas equation with the compression factor, right? Hopefully we remembered that went as the following. P times Vm equals RT times Z. Okay, so we developed that last time. And what we seek to do is find a way to write Z in this empirical way. So that is done in the following. P times Vm equals RT now times the quantity 1, which is the ideal Z value. And we're going to do this as an expansion of powers. So now this is plus a new term, capital B, over Vm, plus capital C over Vm squared. And we could keep going with this thing, plus D over Vm cubed, plus E over Vm to the 4th power, and etc. And we can keep adding more and more and more terms to get a better and better fit to the model. So generally, we're only concerned with these first 3 terms. The first virial coefficient, which is the ideal value of 1, the second, and the third. So we don't typically see this go off to that level. So, and from there, we note here that we're really not changing the ideal gas law. We're just coming up with a different way to write the compression factor, which is the following. 1 plus, and I'll just rewrite that again, B over Vm plus C over Vm squared, and I'll leave it at that. We could also substitute the ideal gas equation into that calculation of Vm, which of course would just be an approximation, right? Because technically we should supply the van der Waals equation, but then we'll just end up in this circular relationship. So we could also write this as 1 plus, and instead of writing B over Vm, I'm going to write B over RT over P, and doing that algebra, that ends up with P over RT, of course, times B. And then now substituting into the next term where we have Vm squared, that would go as P squared over the quantity RT squared times the quantity C. So now generally in this process and in this class, we like to think of derivatives as a way of teasing out relationships. So if we look at the derivative dz by dp, that's going to allow us to tease out how the compression factor depends on changes in P, right? Changes in Z with changes in P. And if I go through and carry that derivative, right? dz by dp of 1 is 0, so that drops out. Taking B over RT derivative with respect to P is going to drop out the P. So that just leaves us with B divided by RT. And then now if we do the same thing on this with the other term, that's going to be 2 times P divided by RT squared times C. So what is the significance of all of that? Well, technically speaking, let me rewrite that. dz by dp, if this equals 0, we have an ideal gas, okay? So as you can see, we didn't get to 0 by taking this derivative. However, we can also impose this other limit as P approaches 0. And so in this case, if we're looking at where this tends to this ideal gas regime, as P tends to 0, this whole term drops out. And so thus, and T will never be 0, right? So thus the only way, or one way to get to ideal gas behavior is as B approaches, or I should really say, because B is, as we'll see, a constant, as B equals 0. So when B equals 0, as P approaches 0, we will have an ideal gas. And as it turns out, there's a special condition that corresponds to B equals 0, and that is known as the Boyle temp, the Boyle temperature. Not the boiling temperature, but right, the Boyle temperature, right, for the gas law. So let's make a graph of what this thing looks like, okay? So recall the equation was Z equals 1 plus B, and I'm going to write this with respect to pressure, P times B over RT plus P squared over RT squared times C. And that's what this equation looks like. So remember, once again, the Boyle temperature, the temperature at which a real gas behaves like an ideal gas, which is achieved when this B constant equals 0. So what that tells us, to get that B constant to equal to 0, it's going to have to be equal to some other things that allow it to be 0 under certain conditions. Okay. So now looking at this compression factor, the perfect gas here is indicated by a Z of 1.0000, right? There's our perfect gas line. So on this x-axis here, this would be 0 ATM, and this might be something like 1,000 ATM, right? We can look at this relationship over a very large value. What I also want to note here, the compression factor scale is not all that large. I mean, like, these increments are probably on the order of like 1.02 and 0.98 and 1.04 and 0.96. So we don't see like huge changes in this compression factor for real versus ideal behavior in gases. If we compress gases by a significant amount, maybe from like 1.0 down to like 0.5 or something, we're going to liquefy those gases. And we will be getting into that soon. So now if we note here, at lower temperatures, what we would discover in this relationship is for a given pressure, right? If you look across this whole pressure range, at lower temperatures, gases behave in this attractive regime, right? Because we're at Z's less than 1. However, at a higher temperature for any given pressure, right across this whole big range, a higher temperature would owe to the repulsive regime. And then finally, we're down to this Boyle temperature. And what I want to point out, you notice when we get to a high enough pressure, the Boyle temperature does take off into the repulsive regime. However, we have to consider this wide scale here. So I'm going to draw a box like around this area. And if we zoom in on that Boyle temperature, you can see the curve is staying very close to the ideal gas line before it takes off into the repulsive regime. You can also see if I zoomed way in even further, like to this little point right there, that none of those temperatures matter, and they're all right at the perfect gas regime. So this range that we're talking here is very low, like on the order of 1 to 5 ATM. So in that low to modest pressure range, we get this ideal gas behavior, which is where we are on planet Earth. As we get way outside of that range, that's where we see this interesting stuff happen. Okay, so we have to figure out how we can achieve this. So I'm just going to point to that arrow and make a question mark. How can we get to this constant B being equal to 0? Well, we can do that by playing with the math. And we're going to attempt to now smash together these two equations of state. So we've got van der Waal and we've got the virial. We're going to see if we can't get them to like go along with each other. All right. So I'm first going to just note that I can rewrite the virial as P equals RT over Vm times this expansion of powers describing Z, and we'll go back to the per Vm basis here. And so now what I want to do algebraically here is try and rearrange the van der Waals equation so it looks something like this. So I am going to factor out an RT over Vm from this equation. So I'm going to write P equals RT over Vm. And now I've got to recover all of this algebra here that I did in the factoring. Well, I factored out an RT from there, so I can just put a 1 on top. And now I'm just going to quickly go through the algebra for you because I want to make sure that we don't get too heavy-handed or long with this. But what's going to end up happening there with the denominator is it becomes 1 over B minus Vm. And if we were to do a quick inspection, right, like if I were to multiply that back through, I would recover that first term. Okay? And so now I still need to factor out an RT over Vm from this term right here. And because I didn't have an RT in there, I'm going to need to have a 1 over RT. So I still have the A. And then now I'm just going to end up with an RT and just 1 Vm because I had a Vm squared that I was able to factor out. And again, quick inspection, if I push that back through to this term, you can see the RT and the RT would cancel. I'd get a Vm squared, and I'd have my A term. OK, well, as it turns out, this chunk right here that I'm going to circle, OK, bubble off. So that is yet again the form of another Maclaurin series expansion. So the Maclaurin series expansion goes as the following. 1 over 1 minus x equals 1 plus x squared. And we can actually keep going with that just like we did up here. So you can see we're like on the right track. And if I call b over Vm equal to x, I can substitute this expansion power into this. Okay, so that's going to go as the following. That's going to be P equals RT over Vm. And now I can replace this whole chunk with the following. 1 plus. Instead of writing x, I'm going to write b over Vm. And now instead of writing x squared, I can write b squared over Vm squared. And we're just going to stop there. We're only going to do 2 terms. And then I still have my minus a over RT Vm. All right, this is looking pretty sweet because now when I compare these, look, they've gotten really, really close to each other. This is awesome. And so you can see I've got a PRT over Vm and a PRT over Vm. So those are equivalent. That's great. So now all I need to do is relate this chunk to this chunk. And you can see here that I might actually be able to get some of the van der Waals parameters, the little a and the little b, to be equal to the virial parameters, the big B and the little c. So I'm going to rearrange this algebraically. So I'm going to take just this chunk over here and write z equals 1 plus b over Vm. I'm going to keep this other Vm term with that so I can see that those will combine. And then now plus b squared over Vm squared. Okay, so combining those 2 terms, okay, I'm going to factor out a 1 over Vm. And now I get b minus a divided by RT plus, and I'll factor out a 1 over Vm squared right here, times b squared. And now if I look at this equation right here, I'm going to highlight all of this now, right? I've got this chunk, b over Vm, and look, I've got this chunk right here. And then now, let's get a slightly different color. I've got this chunk right here, and now I've got this chunk right here. So what that means is we can actually write that the c constant, the virial coefficient c, is actually equal to the van der Waals parameter b squared. That's really cool. That's important. Let's box that off. And now you can see that the van der Waals constant b, or excuse me, the virial coefficient b is equal to this collection of van der Waals terms, b minus a divided by RT. That's really important as well. And so finally, we discussed that this boil temperature occurs when this big term equals 0. So finally, doing the last little bit of algebra, if I set b equal to 0, we can see that 0 equals b minus a over rt. And now doing some very quick algebra here, right? Adding that over to the other side and rearranging, we would get that the boil temperature T boil equals, so again, add that over to the other side and do the algebra, is A over B times R. This is really fun. Look at that. We've got 3 constants equaling some fundamental thing, the boil temperature. So the van der Waals coefficient A over the van der Waals coefficient B over the ideal gas constant. And because each molecule has a different A and B term, each gas has a unique boil temperature, which again, recall that boil temperature, the temperature at which a real gas behaves like an ideal gas over a large range of pressures. So we will calculate some boil temperatures and go over this in more detail in the live lecture. I'll see you then.